quarks have color. Now, this doesn't mean what they look like, but rather the type of strong force charge that they have. So normal charge, electromagnetic charge, comes in two kinds, positive and negative. Gravity has only one kind of charge, which is mass. The strong force actually has 6 kinds of charge. Quarks have colors or charges of red, green, and blue, and antiquarks are anti-red, anti-green, and anti-blue. So all of these colors are the different kinds of charge that's present when you have the strong force. Particles are colorless or white. Baryons have all 3 colors present. So whenever you have a baryon, one of the quarks will have red strong force charge, one will have green, and one will have blue. And just like light, when you combine all the possible colors, you get white light or white strong force sum of charges. Mesons, on the other hand, since they are made of a quark and an antiquark, have a color and an anticolor. So their quark might be red, and then the antiquark would be anti-red. So the Standard Model is the model that brings together everything we know about particles. It combines something called quantum chromodynamics, or QCD, that describes the strong force, and combines that with quantum electrodynamics, or QED, which is all of the theories having to do with the electromagnetic and the weak forces. So when you combine all of these things together, you get the most complete picture of the interactions between particles, and this is called the Standard Model. There's a couple of problems with the Standard Model. Even though it's been very successful, the Standard Model is great at describing the vast majority of particle interactions that we see in colliders. But there are still a couple of problems. One is that the Standard Model doesn't fully describe why force particles have the different masses that they do, and it also doesn't account for gravity. You'll notice that we've listed off all of the forces that have been wrapped up into this theory. The strong force, the electromagnetic force, the weak force. Gravity isn't there. We don't know how gravity, and specifically relativity, plays with the Standard Model. The two are sort of incompatible, and it's important to know how they fit together because that would be necessary for describing things like black holes, where you have all of the matter compacted down into a very, very tiny region, so it should obey quantum mechanics, which is part of the Standard Model, but you also have very strong gravitational forces, and we don't know how to combine those things together. So the Standard Model cannot incorporate general relativity, and this is one very active area of research. People are trying to figure out how to put together general relativity with the Standard Model that describes all of the other forces. And a couple of those theories are things like quantum gravity, or also string theory tries to incorporate all of these different things. So the Standard Model you'll often see represented by a table, and this table describes all of the fundamental particles that we know about. So we have, in this particle, we have all of the quarks, the up, charm, top, down, strange, and bottom quarks. It has the leptons, the electron, muon, and tau, along with their neutrinos. So all of the particles that are in all of the tables that we've looked at so far are made up of these fundamental particles. So we have the quarks, which make up the hadrons, and then we have all of our leptons. In addition, we have the charge or the force carriers, the photon, gluon, the W and Z bosons, which are responsible for the weak force. You'll notice the old graviton is kind of left out because we don't know how that fits into this bigger picture. There's one more particle that needs to be added to the Standard Model, which is the Higgs boson. And the Higgs is thought to explain why some of these fundamental particles have different masses. Why is it that the electron, the muon, and the tau have very different masses? So if we use E equals mc squared, we can convert these energies that are given into masses, and we can see that the electron is much lighter than the muon, which is much lighter than the tauon. And why is this? Why do they have different masses? It turns out that they interact differently with something called the Higgs field. It's a field that goes throughout all of the universe, and different particles interact with it differently. And if a particle has a weak interaction with the Higgs field, then it has less inertia, like the electron, and therefore it has less mass, whereas a tauon has a stronger reaction with the Higgs field. A wave in this Higgs field is called a Higgs boson, and the Higgs boson was first measured in particle colliders not too long ago, and it was a very important discovery, one of the most important scientific discoveries of recent times. So particle accelerators are responsible for much of what we know about fundamental physics and much of what we know about particles. And a particle accelerator is typically an enormous device. Here you can see the LHC, the Large Hadron Collider, and you can see this Large Hadron Collider, a picture of it, where it is located, is superimposed over this picture of the city. It's an enormous set of tubes where you have particles going around in a circle, their trajectories controlled by magnetic fields, and then at certain parts of the circle you have detectors like ALICE, CMS, and ATLAS. And these detectors are massive objects. They have a huge amount of specialized technology in them. They're some of the most advanced pieces of equipment in the world. They're also enormous. You can see a little person here in this picture right here. So they're very enormous, very highly advanced, but the basic idea behind detectors is kind of captured in this comic, where you have some of your stereotypical cavemen, and they are arguing about what is fundamental. So the first caveman says, big rock is the most fundamental particle in the universe. No, big rock is made up of small rocks. Two collider. So they collide two big rocks together. The rocks split, and it says, look, small rock come out of big rock. Small rock fundamental. Small rock is maybe statistical artifact. So they do it over and over and over again to build up statistics. Okay, small rock fundamental. Me told you so. And then someone else says, wait, small rock made up of very small rocks. Very small rock is fundamental. No such thing as very small rock. Two collider. And they collide some very small rocks. Ha! Very small rocks not split. Small rock is fundamental. Just need rocks go faster. Then find very small rock. Sure. And then 10,000 iterations later, Professor, what is a fundamental particle? Anything smaller than what was fundamental a generation ago. And to some extent that is true. Are quarks fundamental? Are they really fundamental? Can you smash particles together hard enough that the quarks split? This is something we don't know. And so that's why scientists are always building bigger colliders. And whenever a bigger collider is built, and more powerful, that can smash particles together harder, we discover new particles, we discover new science, new physics.